Okay, so let's continue with the derivation or discussion of the thermodynamic behavior of ideal Fermi systems. By equation number 7, we have obtained expression for pressure of ideal Fermi gas. Now let's obtain expression for the number density. Okay, number density of the ideal Fermi system. So the number density. Okay, let's take number density. Let me change the color of the pen at least. Yeah. So the number density. Okay, instead of forgetting number density, we will start with the number of particles. The general expression for n we have n is equal to, the expression is z dou by dou z. I think by the time you are familiar with all these standard expressions of log of grand partition function, which is log z. So I can substitute here, that is equal to z dou by dou z, and for log z we obtained that is equal to v divided by lambda cube. Of course gi can be included later if needed. So v by lambda cube f of the Fermi-Dirac function phi by 2 z, that is the thing. Now this is dou. When you take dou by dou z, we are keeping the temperature as constant. So lambda cube and v can be taken outside. So it becomes, this is equal to, we can write this is equal to what happens, we have done it. Let me write the result first, and this is equal to simply v by lambda cube. Finally you will be getting, this is equal to v by lambda cube of f of 3 by 2 of z, f 3 by 2 of z. So this is what we get. And how come that where we have applied a property like a recurrence relation for the Fermi-Dirac what you call function, which is by using z. This is an identity. You can remember this one as an identity or a property of a Fermi-Dirac system. Z into dou by dou z of f nu of z, that is equal to f nu minus 1 of z. So this is a property. Remember this one as a property of what you call Fermi-Dirac system. So I have used that. So we had a z dou by dou z of f phi by 2 of z. So that will be equal to one order less than that. So that is f 3 by 2 of z. So that is our equation. Now by including the degeneracy also, we can write the previous equation as n is equal to, otherwise n is equal to g into v by lambda cube. If you bring back the degeneracy factor gi or gs or simply g into f of 3 by 2 of z. Okay, but we are interested in number density because it's particle density, which is a distinguishing feature of the quantum systems. So I'm writing therefore number density of the system, which we are writing as small n is equal to capital N by v. So you have to take that v to the left side, so that will be equal to g divided by lambda cube into f of 3 by 2 z, or f 3 by 2 of z. So that gives you the second equation of state, we can call that. This is we call that equation number 8. Okay, this is yet another equation of state, okay, which connected. Similarly, and see that you please compare it with the corresponding equation of ideal Bose system. You will see that there is also g by lambda cube g of 3 by 2 z. Okay, so just compare, we will do that. So now another important thing is we are interested in knowing the internal energy of the ideal Fermi system. So let's obtain an expression for the internal energy of the ideal Fermi system. For that, we have to start with the standard expression for internal energy in ensemble formalism, that is U equal to minus dou by dou beta. There are two expressions, minus dou by dou beta of log of the partition function, which is also equal to, by using the identity, you can convert it into terms of temperature, that is equal to kT square dou by dou T. That is our identity. Minus dou by dou beta is equal to kT square dou by dou T, which we have proved in some earlier steps of log of grand partition function. Now we can just substitute for this one, so that is equal to kt square dou by dou t of what is log z. Log z was obtained as g into v divided by lambda cube f of 5 by 2 of z, f of 5 by or f 5 by 2 of z, that is the. And now what you can done is dou by dou t. Okay, so here when you take dou by dou t, it's a partial derivative with respect to temperature alone, so you have to treat z as a constant. Okay, so in that sense you can take f 5 by 2 of z and g v etc outside. And where is that temperature dependence coming in the bracket? That is from lambda, because lambda is equal to, you know, h by root of 2 pi m kt. So in that there is a temperature dependence, so I'm retaining that thing, so I'm doing that. That is equal to kt square v is and then g, then f of 5 by 2 or f 5 by 2 of z also taken out, then dou by dou t of the remaining thing, dou by dou t of 1 by lambda cube, which I can write as 2 pi m kt, I'm inverting it, raised to 3 by 2, okay, divided by h cube. Okay, so that is dou by dou t of this particular factor you have to calculate. And of course you know that is going to be, we have done the same steps in ideal Bose system, so I don't spend much time on that. So which is equal to, that is u is equal to, so on taking the derivative of that raised to 3 by 2 and on, so 3 by 2 kt, this is what you are going to get, 3 by 2 kt g v divided by lambda cube, you get back lambda cube finally into f 5 by 2 of z. Please just refer back or you try to work out this one, it's not difficult, which can be again written as 3 by 2 kt, 3 by 2 kt into gv by lambda cube, can be from the previous expression we can write that in terms of number of particles, that is n divided by f of 3 by 2 z. Okay, for gv by lambda cube I'm substituting from this expression. See, from this expression I'm substituting gv by lambda cube will be equal to, simply you take this one to this side, so it will be n by f 3 by 2 of z. So by that I'm substituting, this is the thing, into f 5 by 2 of z. You will understand we have seen the same steps in ideal Bose system. So finally it becomes of a very standard form, that is equal to 3 by 2 n also is written here, n kt, which is a very familiar expression for us, into f of 5 by 2 z by f of 3 by 2 z. So these are the only things, these two factors are the only things that is additional, okay, compared to this factor for a classical ideal gas. So we are able to obtain finally. So remember this equation, so it's quite easy to remember also now. So this is let me call this equation number 9. That gives you what is known as internal energy of a ideal Fermi system. Or you can say that when you take, you divide by volume, if you divide this one by volume, you will get what is known as energy density. Okay, if you need energy density, you divide by volume, that is energy density, small u is equal to capital U by volume. So you just divide by volume on the right side of equation number 9, you will be getting the energy density if that is needed. Okay, now let me do one more thing using using the previous expressions, that 7 and 8, using equation number 7 and equation number 8. Okay, in equation number 9, you can try out this one. You will get u is equal to 3 by 2. Okay, in place of nkt I'm substituting v by lambda cube into f 3 by 2 of z. Okay, so you can see that was from equation number 7. So let's see equation number 7, you can see this one, this is equation number 7. So where you have got a p by kt equal to g by lambda cube f 5 by 2 of z. So I'm substituting here also, that is equal to v by lambda cube, and that is there, then p lambda cube, we substitute p lambda cube from that, this is from equation number 7 actually, the other one is from equation number 8, p lambda cube by f phi by 2 of z, okay, into, there is already here f phi by 2 of z by f 3 by 2 of z in equation number 9. What happens is that this f 3 by 2 z will be getting cancelled here, here, these two are cancelled. Lambda cube and this lambda cube will be getting cancelled. So what you are finally left out is 3 by 2 of, then v is there, then there is a p there, so that is pv, 3 by 2 pv. So that is, or from this, okay, let me write it here itself. Okay, you can write p is equal to, you can just rewrite 2 by 3 u by v, and what is this u by v? That is the energy density. Okay, so by that you are able to prove that the pressure of a ideal Fermi gas is 2 by 3rd of its energy density. So that is a very similar expression we had obtained, relation we had obtained for classical ideal gas also previously. Okay, so pressure is 2 by 3rd of the energy density. Now moving on, yes, before we go for the comparison, let's also obtain similarly Helmholtz free energy. Any thermodynamic quantities can be obtained. A is equal to U minus Ts, which is equal to U is, okay, you can just write mu n, energy can be written as mu n minus PV. Okay, so it can be written as mu n minus PV, and from 9 and 10, okay, 10 means our see this equation is your 10. Let's call this equation as equation number 10 for the time being. So using those expressions, we can get PV is equal to NKT f of 5 by 2 z divided by f 3 by 2 z. Okay, and also we have already seen that mu is equal to simply kT log of fugacity z from the expression of z is equal to e raised to minus alpha, which is equal to e raised to mu by kT. We have done it. Take a log on both sides, so it becomes log z is equal to mu by kT, or mu is equal to kT log z. That is what I have used here. So mu equal to, so using these expressions, I can write A is equal to simply mu is written as kT log z. Different ways you can end up actually. If you are asked to prove something or you need something, you can do like this. So minus nk, PV is equal to nkt into f of 5 by 2 z divided by f 3 by 2 z. So you can take some nkt as common factor out of that. So it is nkt into log z minus f 5 by 2 divided by f 3 by 2. Of course, they are functions of z. So that is, let me call it as equation number 11. That gives you the Helmholtz free energy. Similarly, you can get entropy. S is equal to U minus A by T, which is finally, it can be obtained as Nk into, you can just please try it out if you have time. Okay, otherwise, just go through this one from any of the standard books. This is just a matter of numerical or algebraic manipulations. So that is equation number 12. So that's about the derivation of the thermodynamics of a system of ideal Fermi gas. Now, before we end up this particular lecture, let's make a comparison of the equation of state of ideal bosons and ideal fermions, so that you will be able to recall better. Okay, all these expressions, all the relevant equations can be recalled better. So I'm going to write one by one for ideal bosons and ideal fermions. You can just compare this one with your notes. So we started with log z, which is Q potential for ideal Bose systems, which was equal to sum over all energy values log 1 minus z e raised to minus beta e. So what was the corresponding equation here? So here it was, we started with log z is equal to, this way I suggest that you learn all these equations this way, so that it's quite easy. You will understand there is a very fine boundary between the behavior of bosons and fermions. Okay, sum over E, there is minus sign is missing. Log 1, instead of 1 minus, it was 1 plus, set e raised to minus beta E. So that I think learning this one is not a problem, but understanding you have to devote your own time because it's conceptual. Okay, equation number 2. Okay, or second, it's not equation number 2, second one. Further, we proved that this log set for both systems was equal to V by lambda cube G 5 by 2 of Z. Okay, and here instead of G 5 by 2 of Z, which is the Bose-Einstein function, we introduce what is known as what? The F 5 by 2 of Z, log Z for boson. We proved that this is equal to V by lambda cube F 5 by 2 of Z. It's not quite easy. Okay, and third equation to compare is where we use G 5 by 2 of Z was defined as sum over L equal to 1 to infinity Z raised to L by L raised to 5 by 2. Whereas here we defined F 5 by 2 of Z, there was a minus 1 raised to L extra, which I told you while we did it, that is sum over L equal to 1 to infinity. You see the similarities here, minus 1 raised to L Z raised to L divided by L raised to 5 by 2. So this minus 1 raised to L makes all the difference between the two special functions. So the fourth equation is that, this is for your knowledge, G nu of Z can be expanded as Z plus Z square by 2 raised to nu plus Z cube by 3 raised to nu plus etc. It goes on. Whereas this F nu of Z is series expanded as Z minus Z square by 2 raised to nu plus Z cube by 3 raised to nu minus plus minus plus minus and so on. Okay, that is a series expansion for that one actually. So equation, then for fifth one, we obtained P by KT for both system is equal to G 5 by 2 of Z divided by lambda cube. Okay, and here in that place you got P by KT, the first equation of state, as what? F 5 by 2 of Z. Of course you can add the internal degeneracy also here, that is optional, that you can keep it there. Okay, that is first equation. Then we got equation for number density small n is equal to n by V. We got it, that is equal to G, instead of G 5 by 2 Z, this is G 3 by 2 Z, because we took a derivative dou by dou Z with respect to Z we are done. So we got by the property, we got this is equal to G 3 by 2 Z divided by lambda cube. That is quite easy to remember. Here also we got small n is equal to F 3 by 2 of Z divided by lambda cube. Of course G can be added, degeneracy, interdegeneracy can be added along with both. Then see, another expression was okay, the internal energy U or U by V, okay, whatever it is, U by V, the energy density was obtained as 3 by 2 KT, okay, G 5 by 2 Z divided by lambda cube. Here correspondingly you got that is equal to U okay, U is equal to, the energy density was equal to 3 by 2 KT F 5 by 2 of Z divided by lambda cube. Okay, similarly you got another expression, the internal energy U can be proved as 3 by 2 NKT into, to compare with the classical ideal gas equation of state, into G 5 by 2 divided by G 3 by 2. All are functions of Z. So here similarly you can get that U, internal energy U is equal to 3 by 2 NKT. Just what you have to do is that you have to replace G with the F 5 by 2 of Z divided by F of 3 by 2. Right. Similarly we got okay, PV is equal to NKT. We could prove this one there. PV equal to NKT G 5 by 2 of Z divided by G 3 by 2 of Z. Same manner here you will be getting PV is equal to NKT, what do you call G, instead of G it is F 5 by 2 divided by F 3 by 2. Same manner A is equal to 10, okay, the Helmholtz free energy A is equal to NKT into log of fugacity minus what is that, G 5 by 2 divided by G 3 by 2. That was the expression for bosons. Here it will be A, the Helmholtz free energy is equal to same nkt into log of fugacity minus f3 5 by 2 divided by f3 by 2. So that is the comparison of the equation of state or the corresponding derivations in the case of what we call ideal Bose and ideal Fermi systems. So hope that is enough for the time being, and see that you learn both these cases on comparison. It will be quite easy, write and practice. That will be helping you to understand better. Now in the next lecture we will be discussing how fermions behave at absolutely low temperatures, or what will be the behavior of fermions at absolute zero. That will give some idea regarding some new concepts like Fermi energy, which you are already familiar, okay, in semiconductor physics. So we'll do that. Thank you.